Welcome everyone, and thank you so much for joining us today for the Grasp on Robotics series. As a quick reminder, this and previously recorded talks can be found on our YouTube channel and website. Also, throughout the talk, please submit your questions using the button at the bottom of your screen. These will be answered during the Q&A panel at the end of the talk. Now, I would like to introduce our Grasp faculty host for today's talk, Dr. Nikolai Matny, Assistant Professor at the Electrical and Systems Engineering Department within the School of Engineering here at the University of Pennsylvania. Thank you very much.
Thanks, Gabby. Good morning, everyone. I'm Nikolai Matny, as Gabby said, an assistant professor in the Department of Electrical and Systems Engineering. And it's my pleasure this morning to introduce Professor Marco Pavone of Stanford University. And my dog decided to start barking just this instant. So Marco is an associate professor of aeronautics and astronautics at Stanford University, where he's the director of the Autonomous Systems Laboratory and co-director of the Center for Automotive Research. Before joining Stanford, he got his PhD from MIT and then spent some time at National Jet Propulsion Laboratory in Pasadena. Marco's research broadly lies at the intersection of control theory, robotics, optimization, and operations research, and he's made groundbreaking contributions to the analysis, design, and control of autonomous systems, particularly in the areas of self-driving cars, autonomous aerospace vehicles, and future mobility systems. Now, Marco's won too many awards to list, including pretty much every early career award you could hope to win, including the prestigious PCASE Award from President Barack Obama and a NASA Early Career Faculty Award. He's also been identified by the American Society for Engineering Education as one of America's 20 most highly promising investigators under the age of 40. And on top of all that, his work's been recognized with a slew of best paper nominations or awards at premier controls, robotics, and intelligent transportation conferences. And now, without further delay, Marco, the floor is yours.
Thank you very much, Nick, for the kind introduction. It's a real pleasure to give a talk at the GRASP seminar. All right. So my lab, the Autonomous Systems Lab, focuses on the design of planning and decision-making algorithms for autonomous robots. A key application domain in my research is space robotics. Specifically, as a research technologist at the NASA Jet Propulsion Laboratory before joining Stanford, I worked on optimizing the entry, descent, and landing of Mars rovers on the Mars surface. I also been working on the design of robotic mobility platforms for the exploration of very low gravity bodies where traditional mobility systems based on wheels do not work well anymore. One of the critical aspects of moving on very low gravity bodies is that the surface of such bodies, which include, for example, asteroids and comets, is very complex. On the left-hand side, you can see the surface of a comet. In particular, in collaboration with the JPL, have designed an internally actuated hopping robot that can move on the surface of an asteroid by either hopping or tumbling. And I've been testing this platform on a fairly unique microgravity testbed that you can see here on the right, where the microgravity dynamics are emulated by using a gantry system that suspends the internally actuated robot in black through a gimbal system. Through collaboration with NASA AIM and Mark Witkowski at Stanford, I'm working currently on the problem of grasping and manipulated objects in space. Here I'm showing tests at the NASA AIMS, where the zero gravity environment of space is emulated by using air bearings over a very flat granite table. The arms that you can see on the blue cubic robot is equipped with gecko-inspired grippers. These are grippers equipped with pads that, by exploiting directionally aligned microfeatures, become adhesive when loaded in shear stress. A flight-qualified version of the gripper that you can see on the right has been sent to the International Space Station in July 2010. Is going to be connected to one of the satellites inside the International Space Station called the Astrobe later on at the beginning of next year. And we'll go for the experiments on the International Space Station in February 2021. So this is quite exciting. A key point here is that increasing the level of autonomy for space robotic systems is challenging due to the uncertainty of the environment, coupled with the complex and oftentimes highly stochastic dynamics of space robots. However, as a redeeming factor, space robots do not have to deal with the intelligent forms of life, that is, humans. Interacting with humans represents a key challenge for robot autonomy. And indeed, the interaction with decision-making will be the key focus of my talk today. Consider in particular the case of self-driving cars, with understanding that everything I'm going to say today applies more broadly to any autonomous robotic system that has to operate alongside a human. Interaction with humans entail very complex interactions. They are oftentimes the result of a complex and sometimes aggressive negotiation. In other words, autonomous robots should be able to negotiate their behaviors with the humans, similar to how we as humans do with other humans on the road for safe and efficient driving. Or in other words, a key capability for autonomous robots in order to navigate complex interactions, such as the one depicted here, where vehicles want to merge on the road, is to exhibit what I refer to as proactive decision-making. That is, they should be able to proactively interact with other agents to infer their intents, while concurrently exploiting this information to take actions that then account for agent responses. Now, my key approach to enable proactive decision-making is model-based, whereby a probabilistic understanding of the interaction dynamics is used as the basis for policy construction. This is in contrast to model-free approaches, where human action possibilities and relative likelihoods are learned only implicitly encoded in a policy that is directly learned from data. And the rationale here is that by decoupling action-reaction prediction from a policy construction, we can achieve a level of transparency that is typically unavailable to model-free approaches. So bottom line is that in my work, I exploit a model-based approach. In a model-based approach, the first step is to develop a model to predict human intent and its corresponding trajectories. And my work in this area is guided by 5 key considerations or desiderata. First of all, from the perspective of decision-making, we want to design a model for human intent prediction that allows us to reason in terms of how a human would react conditional to what a robot might do in the future. Second of all, at this layer of the decision-making hierarchy, we are tackling problems with a time scale of about 1 second. This is different from higher level decision-making that reason in terms of multi-second decisions. For example, should I change a lane or should I negotiate an intersection? And this is different from lower level control, such as for collision avoidance, that typically requires computations at the millisecond level. Third, at this level of decision-making, the uncertainty that characterizes human behavior is in general multimodal, corresponding to the drastically different possible human responses with respect to a robot action. To be concrete, consider on the right-hand side the case whereby a robotic vehicle depicted in white wants to exchange lane with a human-operated vehicle depicted in blue. So if the robotic vehicle were to accelerate, depicted with a long white arrow, then the human might react with the 2 distinct modes. The human might decelerate, most likely, as represented by the shorter yellow arrows, but it might also be aggressive and accelerate. This is what I refer to by multimodal prediction, and it's a very important point for proper human intent modeling. Fourth, we want to be able to account for history dependency. And if you're familiar with the Markov decision processes, you know that this computationally is a challenge. The reason why we want to be able to reason about history dependency is in order to be able to uncover latent behavior, such as aggressiveness or alertness. And finally, we would like to have a framework that is as interpretable as possible in order to ease debugging and also to gain trust into the overall methodology. Now, to infer human intent, typical approaches such as inverse reinforcement learning that I refer to as ontological or theory of mind postulate some structure on the human decision-making process. For example, in the form of a cost function that we postulate the human is trying to optimize. But this postulated structure is sometimes difficult to reconcile with how human drivers actually operate. Humans are neither adversarial, they're neither nor cooperative. And this fuzziness of behavior is difficult to reconcile with a theory of mind approach that is ultimately rooted in game theory. We've thus investigated whether, given enough data, we can learn the probabilistic structure of an interaction without reasoning or placing any assumption on how humans make their own decisions. We refer to this approach as a phenomenological because we are directly learning the probabilistic structure of an interaction without postulating any structure on human decision-making. Our key idea in order to do so is to exploit recent work from the generative modeling community. Where our work differs from the norm, however, is that since we're interested in interactive behavior, we're interested in making prediction of the future based on observations from the past, but also we want to reason about how someone might respond contingent on what an autonomous robot might do in the future. Explicitly, we want to learn a probability distribution P of future robot actions U, H, T plus 1. The subscript H denotes human, R denotes robot, U is the control X state, T plus 1 is the next step. So we want to learn from data a probability distribution about the next action for the human, conditioned on the history of the interaction, namely the relative state X and the relative control U. The relative state, for example, could be relative speed or relative positions in the previous T time steps between the robot and the human. And critically, also conditional on a candidate future robot action. Conditioning on the on history lets us infer things about human driver behavior, such as aggressiveness or alertness, while conditioning on a candidate future robot action allows us to capture the interactive aspect of an interaction. In practice, we use a conditional variational autoencoder model in order to learn such a distribution. And the way that this model, once it's trained, works is as follows. So here I'm showing the case of a pairwise interaction between a human-operated vehicle and a robotic vehicle. On the x-axis, we have time. On the y-axis, we have longitudinal acceleration. A solid line depicts the dynamical quantities that have happened in the past, while a dashed line depicts the future. Blue is the acceleration profile for the robot. Red is the acceleration profile for the human. So you see that for the first 0.7 seconds or so, both the human and the robot have zero longitudinal acceleration, so they're going at a constant speed, side by side. Then the way that we use this model is as follows. Say that the robot is going to use a candidate robot action sequence whereby it's first going to accelerate as depicted by the dashed blue line, then it's going to coast at constant speed, and then it's going to decelerate. with this conditioning, we then sample the generative model that we have trained from data to sample possible human responses. And here you see a bunch of lines between yellowish, brownish, and bluish that depict the possible human responses in terms of longitudinal acceleration. In most cases, we will predict that a human decelerates, but in some cases, it turns out that we predict that a human accelerates, because maybe in the training data, we have also observed some aggressive drivers. We've extended this framework to being capable of predicting future trajectories in a multi-agent setting, so with multiple pedestrians, multiple vehicles on the road, and so on. And most importantly, to be able to ingest as conditioning variables a vast set of heterogeneous data. From dynamical information, clearly a pedestrian behaves in a way that is different from a biker, as well as maps encoding information such as road geometry and road crosswalks, all the way to human silhouettes. The end result is a trajectron plus, a generative trajectory forecasting model that explicitly reasons about agent dynamics, yielding state-of-the-art performance on a variety of real-world datasets. Specifically, we tested the trajectron plus against a number of deterministic and generative baselines, and with respect to a number of different evaluation metrics. And we show that consistently trajectron plus quite significantly outperforms the state-of-the-art. All the numbers about the comparisons are given in the ECCV paper we have recently published. I will point out that we participated in a challenge by autonomy, that is a self-driving car company, which entailed using the new scenes dataset, which is a set of scenes taken from the streets of Singapore, with a number of interesting real-world interactions. And we were one of the top 3 teams. Importantly, here, I would like to point out how critical it is to condition not only on the dynamical history of the interactions in terms of relative states, but also in terms of additional information, such as a map that is encoded through a CNN. Specifically, at the top, you can see the prediction. Here, the data is from the new scenes datasets as well. So here you can see predictions for vehicles at an intersection where you have cars and you have also pedestrians denoted by little dots. Let's focus on the red vehicle on the top left in the top figure. The white line depicts ground truth. The sequence of ellipses that depicts the confidence sets for our predictions. Here on the top, I'm showing the case whereby we are only conditioning on the previous 2-3 seconds of dynamical interaction in terms of relative speeds, relative positions, and so on. And as you can see, the prediction actually undershoots the ground truth. But once we add actually the conditioning with respect to the map geometry, as depicted at the bottom, we see that now the predictions nicely align with the ground truth. And this is something that we observed consistently in our evaluations throughout a number of data sets, from the very standard ones in this field, such as the ETH dataset, to other datasets such as the new scenes dataset, and more recently the LIFT dataset. All the code, models, and data is available on our GitHub page. So the key takeaway here is that the phenomenological models, and in particular deep generative models, achieve a state-of-the-art performance. Until 3-4 years ago, zero-mind approaches were actually the model of a choice for this type of applications. But actually, by now, phenomenological models, and in particular trajectron plus has emerged as a state-of-the-art tool. Now, in my lab, we care about decision making. So at the end of the day, what really matters to me is how do we use this model for the purposes of interaction-aware decision making? Well, the way we use this model for decision making is relatively simple. What we do is to look at a family of action sequence candidates, so basically motion primitives. In actuality, for the case of self-driving cars, we look at about 4,000 action sequences. And for each one of them, we generate a family of possible reactions from a human by sampling our CVA-based generative model. Then we score each action sequence according to an aggregate cost function comprising a number of terms, for example, reflecting the fact that we want to fulfill the task as quickly as possible, but also want to avoid collisions and so on. We drive the first chunk of it, and then we replan in a receding horizon fashion. This process is highly parallelizable, and in particular, we leverage a GPU implementation. And this allows us to reason in terms of 100,000 responses per computation cycle at about 3-4 hertz. So it's pretty fast and compatible with the real-time performance. Now, something important that I would like to highlight is that when we score the action sequences, we consider average performance. So we sample a bunch of human responses, and then we take the average of the resulting reward. We do have distribution information, however, so a natural question would be, how do we account for also events in the tail of such a distribution? Specifically, how do we replace an expectation operator with a risk measure rho in order to reason also about events of low probability but detrimental outcomes? So this is a fascinating topic, both from a modeling standpoint and a computational standpoint, that I won't go into the details now, but you can find some of my thoughts in a sort of position paper I brought a couple of years ago with a former postdoc of mine, Ani Majudmar, now at Princeton. Okay, so let's see how all of this works. So we have validated this framework by using a human-in-the-loop driving simulator based on a virus VTD, which we use in order to train the models and then to test the models and the decision-making logic. Specifically here, I'm showing the setting whereby a robotic vehicle and a human-operated vehicle want to exchange lane before the road splits. Here we are considering a pairwise interaction, but actually we do have extensions that also account for interactions with multiple agents. On the left-hand side, you can see predicted human responses in terms of longitudinal acceleration and longitudinal velocity for a given candidate future robot action. As usual, the human-driven vehicle, which is operated by student by using a hardware-in-the-loop human-in-the-loop simulator, is depicted in blue. The robotic vehicle that runs our algorithms is depicted in white. So here you can see that there are some interesting behaviors that emerge, like, for example, the white vehicle nudging a little bit on the other lane in order to disambiguate the intent of the human. And overall, you can see that the interaction is relatively efficient and safe. So this is great until disaster happens. So this is a case where the human drives erratically by swerving into the robotic vehicle. So this is a situation whereby the human behaves in a way that defies the prediction of the model. Rarely, but sometimes it happens that the human defies the CVA-based prediction. Now, I will claim that probabilistic planning, even with fairly sophisticated interaction models, such as the one I presented before, can lead to unsafe behaviors necessarily for three main reasons. First, probabilistic predictions are probabilistic, so we might get it wrong. Also, as humans, we make probabilistic predictions about what other people do around us, and sometimes we do get it wrong. Second of all, at this level of the decision-making stack, we model collision avoidance as a penalty term in an aggregate cost function. And this can cause conflicting objectives depending on how you prioritize the many different penalty functions you have in a cost function. And finally, planning at 3 Hz is ultimately too slow to ensure safety. I mean, you really need a reactive component that acts at a much higher frequency. So the key question here then is, how do we integrate the safety assurance within a probabilistic performance-centric planning framework? More explicitly, the big conundrum is, how do we strike the right balance between safety and efficiency? This is probably one of the most central questions in the field of interaction-aware decision-making. Explicitly, high-level planners typically leverage probabilistic reasoning to promote efficiency at the cost of safety. While on the other hand, low-level planners promote safety by leveraging worst-case reasoning at the cost of efficiency. Ideally, you would like to be maximally safe and maximally efficient, so where the star is. But in practice, how do we best trade off the performance of a safety-centric planner, depicted in orange, or a performance-centric planner? So the key challenge is how to glue a safety controller with a higher level probabilistic planner in a way that does not unduly impact performance. And in fact, I would claim that in the academic literature, such an interaction among different layers of the control and decision-making hierarchy is often overlooked. So what I'm going to discuss now is, how do we make this gluing principle in such a way that it doesn't happen at a very late stage in the design process by just relying on a leap of faith. Specifically, I will first discuss how to design the safety controller, and then how the different layers of the decision-making stack can be glued. Considering low-level collision avoidance, there are, of course, several methods to promote safety. For example, potential fields, constraint optimization, libraries of emergency maneuvers, and so on. But the key point here is that all these techniques do not account for interactions with a sentient agent, that is, with a decision maker such as a human. Thus, they are quite difficult to glue with a decision-making stack that strives to enable smooth negotiation through probabilistic reasoning. In our work, in order to account for interaction also at the controller level, we harness the tools of Hamilton-Jacobi reachability. Now, Hamilton-Jacobi reachability is, in the context of planning, is often interpreted in a forward open loop sense, whereby human dynamics, the blue vehicle here is the human operated vehicle, the human dynamics are propagated forward in time, and the resulting set, referred to as the forward reachable set, is used as a static obstacle that the robotic vehicle in red should avoid. This certainly leads to safe strategies, but is oftentimes over-conservative. So what we do instead is to rely on the notion of a backward reachability, whereby the joint dynamics between the human-operated vehicle and the robotic vehicle are propagated backwards in time to account for the closed-loop interactions between the two vehicles. The resulting set basically encodes the notion that you do not want to put yourself in a situation that you cannot recover from. Basically, you don't want to be boxed in. And I would claim that, for example, this is how I ride my motorbike as opposed to my car. When I ride my motorbike, since of course a collision could be much more dangerous, I'm much more careful in not putting myself in a situation where I'm boxed in. And so if a human were to act erratically, perhaps because distracted, it might lead to a collision despite what they do in order to avoid such a collision. So I have this idea somehow that in my mind, I compute reachable sets when I ride my motorbike. Now, more formally, the backward reachable set is defined as a set of avoid states for which there exist strategies for the human that for all inputs of the robot will lead to collisions. And of course, you want to be outside of this avoid set. These sets can be computed by solving the celebrated Hamilton-Jacobi-Isaacs partial differential equations, which gives as a solution the value function V that allow us to compute a backward reachable set as its 0 sublevel sets. This computation is hard, very hard in general, but the good news is that it can be done offline. Now, the traditional optimal robot avoidance control in the context of a Hamilton-Jacobi reachability then entails switching to the optimal control U star R whenever near the backward reachable set. The optimal control U star R is the control that offers the greatest increase in the value function you want to get out of the avoid set as quickly as possible, assuming a worst case actions by the human driver, denoted as UH. So the way it works then is that whenever the two vehicles are, the joint dynamics are close to the avoid set, then we switch to the Hamilton-Jacobi controller. And here you can see an example of how that would work, again, in the case of traffic weaving. The green vehicle here is the human operated vehicle that swerves into the robotic vehicle in red. The robotic vehicle switches to the Hamilton-Jacobi safety controller. And what it does in this case is to stop, which is safe, but of course not really efficient. If every time a vehicle were to behave in a way that is a little bit erratic and the autonomous vehicle were to stop, that certainly would be safe, but from a mobility standpoint would be a disaster. Nobody would take a ride on that vehicle. So what we did was to find a way to incorporate Hamilton-Jacobi reachability in a way that does not unduly impact performance. And this is the crucial idea. Specifically, the idea is that rather than switching to the optimal avoidance controller, as I showed you before, we optimize in terms of safety-preserving controls. The set of safety-preserving controls represent a set of robot controls that ensure that the value function is non-decreasing. Now, this set, in general, leads to complex, non-convex optimization problems for planning. So to enable computation times at 100 Hertz, we consider a linearized version of this set around the operating point. So the way we glue now the higher level decision-making module with the low level control is by solving an NPC optimization problem, which is quite standard in that what we want to do is to penalize the tracking error with respect to a reference trajectory computed by the higher level decision-making module, for example, by using the decision-making logic that I presented before, subject to linearized constraints about for the vehicle dynamics, stable handling envelope constraints, control constraints, but with the crucial inclusion of an instantaneous interaction safety constraint whenever near the backward reachability set, the avoid set. So basically, the idea is whenever the joint dynamics are close to the avoid set, we add an additional constraints boxed in red, where we force the control to be taken only from the set of safety-preserving controls. Those controls that ensure that, at the very least, you do not make the situation worse. You do not ensure that you get out of the avoid set as quick as possible, as the optimal Hamilton-Jacobi reachability controller would do, but at least you don't make the situation worse. Of course, we also add a bunch of slack variables in order to make sure that this problem is consistently feasible. I'd like to point out we've also investigated the formulation where the value function is added also to the cost function in order to give the controller an element of foresight in that you don't want, predictably, you don't want to put yourself in a situation where you're boxed in. The overall problem is a QP, which is solved at about 100 Hertz by using the operating split quadratic programming solver. So putting everything together, the overall decision-making and control stack that, again, was developed for the case of self-driving cars, but applies more broadly to general autonomous robots, entails, on the left-hand side, a high-level interaction planner that produces nominal trajectories through a generative model of a human intent at about 3-4 Hertz. On the right-hand side, we have a reachability cache that is pre-computed offline that encodes a notion of relative states that are unsafe, that is, that might lead to collisions despite our best effort. And then a low-level MPC-based safe tracking controller that executes controls that minimally deviate from the planner's choice if the vehicles approach the set of unsafe states. So that's how we glue high-level probabilistic-based decision-making with a low-level worst-case-based control. And the key point here is that we're reasoning about the interaction throughout all levels of the decision-making and control hierarchy. So this sentiment of reasoning, of accounting for the fact that we're dealing with a sentient agent is pervasive through the entire decision-making hierarchy, which means that basically both the low-level controller and high-level controller are aligned. So we tested the full control pipeline on a full-scale self-driving car that I have at Stanford in a lab that I co-direct, the Center for Automotive Research at Stanford. So what we do with these tests is to stress test the algorithms. The car that you see is a fully autonomous, so all perception, decision-making, control, intent prediction, and so on is done on board. And that the role of the human-operated vehicle is taken by a small RC car with a mast that you see with a white flag. The reason why we use the white flag on top of the RC car is to make sure that the RC car is visible from the lidars on top of the self-driving car. And so the RC car takes place basically accounts for the human operator. The RC car is remotely controlled by a student. And what we ask the student to do is to drive erratically. So here is a case whereby the human drives nominally, meaning going straight for a few seconds, but then erratically swerves into the autonomous vehicle. So here you see that now the autonomous vehicle nicely recovers from this dangerous maneuver by doing a smooth handling of responsibilities across the decision-making stack. So the interaction is very uneventful, and that's the point of it. An interaction is also relatively high speed, is about 15, 20 meters per second. So let's go back to the previous plot where we plotted the safety versus efficiency conceptually. Let's see how we do in terms of experimental data. So on the right-hand side, I have a plot where I show results from the experiments, specifically the ones with the X1 robotic vehicle I showed in the previous slide. Again, we have efficiency and safety. I mean, we could discuss at length how we measure safety and efficiency. Here we measure safety by using a metric related to how much we penetrate the avoid set, and efficiency by measuring the amount of excessive acceleration that we have for the vehicle. That is basically a measure of occupant discomfort. So the yellow dots, and I do not display the numbers here because they're not particularly meaningful, but they're given in the IGRR paper that is linked in the previous slide. The yellow dots reflect the results for a controller that is based on Hamilton-Jacobi reachability. So whenever near the avoid set, we abruptly switch to the optimal Hamilton-Jacobi controller. So I call this a pessimistic approach because all of a sudden we go from probabilistic reasoning to worst case reasoning. In red, I consider the case whereby we do not equip the higher level decision-making module with the low-level control module. And in green are the results of our proposed methods, whereby we glue high-level decision-making, low-level control through this MPC tracking controller. And as you can see, experimental performance, so this real data, shows that actually we strike a good balance between the safety of a pessimistic decision-making stack with the efficiency of an optimistic decision-making stack. So it was quite exciting. Related to the idea of infusing safety assurances within those components of the autonomy stack that rely on data-driven techniques, I've recently kicked off a fairly large center sponsored by NASA on safe AI for future aviation systems, where we're currently focusing on three main thrusts. The first one is offline assurances through robust and more structured learning. The second one entails online assurances through runtime monitors and recovery methods, in part inspired by the work that I presented today. And finally, airspace control techniques for the setting where some of the aircraft may be autonomous, that is driven by AI. Takeaway message then is that in my mind, safe and efficient interaction where decision-making requires a principled blending of probabilistic and adversarial planning. This blending is often overlooked, but there are a number of interesting intellectual and very practical challenges in how to glue these different styles of reasoning. I'd like to conclude my talk by giving you a brief overview of current and future research directions in my lab on this topic along three main dimensions. First of all, representations of forecasted trajectories that are more efficient to use in downstream control. Second, how to account for uncertainty sources that stem from the upstream perception module. And finally, how do we add logical structure into the models to make predictions more structured? For example, to account for the rules of the road as an additional conditioning variable. Let's start with the representations for control. That is, in general, a topic that is growing in terms of interest in my lab. So nearly all methods in trajectory forecasting predict individual trajectories for each agent in the scene. I refer to these individual trajectories as tracklets. They're basically a sequence of waypoints. So the output structure is a sequence of waypoints for the future trajectories of the different agents in a scene. This is a very natural output structure to provide. However, this representation is not really the most efficient to use in downstream robotics tasks. We saw before that the way I do decision-making is almost by exhaustive search, by using a bunch of motion primitives and then sampling human responses. So it's computationally intense and in a way not super elegant. So the question is, can we devise more efficient representations for the forecasted trajectories that are more conducive to planning and control? To address this question, we have recently proposed to represent intent prediction according to a system theoretic formalism. Specifically, the scene is modeled through a linear time varying system, where the state is the concatenated state of all the agents in a scene, and then control is the robot control, UR. Explicitly assume that we have three agents in the scene, the robotic vehicle that we do control, another human-operated vehicle, vehicle 3, and a pedestrian, vehicle 2. Then the state of the system will concatenate the state of each one of these agents. So what we want to learn are the off-diagonal components depicted in green, which basically model agent-agent interactions. And also, we want to learn some parts of the input matrix B that allows us to reason in terms of how a robot action influence the behavior of a scene. As a result, the CVAE now produces as output structure a mixture of linear time varying systems, where each component linear time varying system models a high level latent behavior. So we have a more structured representation. And we've shown that actually with this more structured representation, we lose very little in terms of prediction performance. But on the other hand, the integration of this output structure with the downstream control is dramatically simplified, because of course you can plug a linear time varying structure with any MPC control scheme of your choice. And actually we show that we could reduce dramatically computation times, even without using a GPU implementation. And as I said, the learning representation that are most suitable to control is indeed a growing research direction in my lab. And here I just show an example that we recently, actually this week, presented at Coral. Related to this topic, we are also working on accounting for uncertainty sources that stem from upstream perception modules. Specifically, we are looking at how to propagate perception uncertainty through trajectory forecasting. For example, in the image on the left, I'm showing how each object has an associated classification score. Currently, in most trajectory forecasting module, this information is not really used. So it is really of interest. That's what we're working on how to propagate this uncertainty all the way to trajectory forecasting, and of course, how to co-design the perception module with the trajectory forecasting module. And complementarily to this, the outputs of a perception module are typically quite noisy, as I'm showing with all the flickering levels in the right video. So we're also working on how to robustify trajectory forecasting against this noise. And finally, we've worked on how to add logical structure into our predictions. For example, to account for rules of the road as additional conditioning variables. Specifically, we have developed a framework that express logic formulas, specifically signal temporal logic formulas, in the same computational graph paradigm that is used for deep learning. So this allows us to express logic, basically symbolic reasoning, in the same language that is used for deep neural networks. And we plan to exploit these results, and actually we've already been exploiting these results in a couple of ways. First, we can now jointly optimize for both prediction performance and robustness with respect to a given signal temporal logic specification during training, thereby embedding logical structure into the model. For example, projecting the predictions in a way that are cognizant of the fact that humans typically obey the rules of the road. And second, verifying the logical properties of the model and detecting anomalies after training. So I think this is a fairly interesting approach because it bridges the gap between symbolic reasoning and neural network reasoning. So my final takeaway message is that in my mind, next generation trajectory forecasting method should account for interactions with other modules in the autonomy stack, in particular downstream control, and should be capable of capturing additional structure to further improve accuracy in the predictions. So to conclude, generative models have become a state-of-the-art tool for trajectory prediction. We have recently published a survey paper. If you don't want to go through the entire paper, which is basically a tutorial, you can just read a blog post about this research. Yet, generative models are quite difficult to integrate with other modules in the autonomy stack. So my research in this area, as I mentioned, is to build the representations that are cognizant of downstream control applications. I'll show you one example, but there are also other ways to do it. Enabling a tighter integration between perception and trajectory prediction, and finally adding logical structure to models. With that, all the code for the work and that I presented today is available on my GitHub page. And I would like to spend a minute to thank my collaborators, primarily Karen Leung and Boris Ivanovich on the top left of this slide. They were the main authors behind most of the work that you've seen today. Collaborators at the Toyota Research Institute, in particular, Nikos Arechiga and Adrian Gaidon, and my collaborator and co-director of CARS, Chris Gerdes, here at Stanford. And of course, my funding agencies, in particular for this work, TRI and ONAR. Thank you very much for your attention, and I'll be happy to answer any questions you might have.
Okay, thank you, Marco, for a really great talk. That was just very broad and also very interesting. So what we're gonna do now is turn things over to our panelists. If they can unmute both their cameras and their microphones, great. So what we have joining us today is we have George Pappas as well, who's joining us, and we also have a first-year graduate student, Feng Jun Yang, who is a first-year graduate student in my group, who also did his master's with Marco's group at Stanford, as well as Lars Lindemann, who just joined George Pappas's group as a postdoc. So I'm going to turn the floor over to them, who are going to ask both questions that they came up with, as well as questions that came in from the audience. And if there's anybody in the audience who has any questions, please type them in to the chat, to the Q&A window, and we'll ask them to Marco. All right, turn that over.
All right, so I have a question related to the safety controller that you have. It reminded me a little of barrier functions. So I was wondering if the Hamilton-Jacobi reachability sets that you have there define a barrier function in the way, or if there is a connection between them that you see over there.
There is a connection, but they're also a little bit different in that the Hamilton-Jacobi reachability really encodes this notion of backward propagating the joint dynamics in order to account for action and reaction responses. So basically, it allows us to reason about interaction with a sentient agent. So it allows us to reason about interactions with another agent that is going to respond to our actions.
Right, so it's basically a step that you put before, and then based on that, you get your function v, right? And that defines then a barrier function, I guess.
Yes, you can do it that way. Once you do the computation, yes, you can do it that way, because basically the way we use it is in a way similar to what you would use with the CBF. That is basically to reason in terms of control that gets you out of that set as quick. Well, in the case of traditional Hamilton-Jacobi reachability, you want to get out of the set as quickly as possible. In the case of safety-preserving controls, you want to reason about controls that do not make the situation worse. So basically that you don't decrease the value of the value function. So the meaning of the value function is a bit different, and how it is computed is a bit different, but then how it's used, it has a lot of similarities with the CBFs, yes.
Okay. I have a follow-up question now that we're on the slide about the function f over there. How is it modeled? What does it?
Yeah, so these are actually the joint dynamics between the vehicle and, so this is an excellent question. These are the joint dynamics between the vehicle, the robotic vehicle, and the human-operated vehicle. So for the robotic vehicle, we use a half-car model that is a fairly sophisticated model to model a car. And for the human vehicle, we use a dynamically extended unicycle model. So the model together is, and then we write the joint model in relative coordinates. So x relative will be the relative state, so the relative position between the two vehicles. So the model is 7-dimensional, which is already quite large for Hamilton-Jacobi reachability. So here there is an interesting aspect. When we first did the tests of this control procedure on the X1 self-driving car behavior, in order to save one state, so basically one dimension, in order to speed up the reachability computation, we did not model the slew of the front tires. So basically we assumed that the front tires could steer instantaneously. They could go from full left to full right instantaneously. Which if you think about, that means that you're giving, you're assuming that the robotic vehicle is more capable than what really is, has more control authority than what really is. So we said, okay, but maybe this doesn't make much of a difference. In X1, going from full left to full right takes about 0.7 seconds. Turns out that when we did experiments, this optimistic view of the dynamics of the robotic vehicle gave rise to, in a number of situations, to unsafe interactions, because the vehicle thought it was able to get out of a difficult situation more quickly than what was actually possible. So actually we went back to the drawing board and actually we added the dynamics for the front tires. So it's just one example about how actually experiments, meaning when the rubber hits the road, are quite important in this line of research. Now, and I want to stop because I recognize that this answer is a bit long, but your question was very useful and insightful. I said that these are basically the joint dynamics between the robotic vehicle and the human operated vehicle. So basically here we are considering pairwise interactions. But in general, on the road, you want to reason about interactions with multiple agents. And 7, 8, you're really pushing the boundary of what you can do with Hamilton-Jacobi reachability computations, even if you do it offline. So forget about doing it with 2, 3, 4 vehicles, at least exactly. But we have extended with the ICRA paper earlier this year, this work to setting with multiple agents, say 6, 7 agents, by using decomposition. So by using actually a bunch of pairwise interactions between the robot and each one of the other vehicles, and then merging them in a relatively clever way. So we can actually extend this work to the multiple agent setting, at least for interaction with 7, 8 agents, if you really want to do it in real time. Real time for me means about between 3 and 5 hertz. For the decision making, and for the MPC controller about 100 hertz, just to pin down the computation times. And now you will say, okay, but in general, on the road, you have interaction with, say, 50, 100 agents. Well, okay, but on the other hand, do you really need to reason with this sophistication with all the agents on the road, meaning also with the ones that are, say, 200, 300 meters in front of you? So the way I view it is that you would have a family of models whereby for the vehicles close to you, you really reason about the action-reaction dynamics. But for the ones that are farther away from you, you can use the simpler models all the way to very simple models, such as the intelligent driver model. Mm. So sorry for the long answer, but your question was exactly on point.
That was very interesting, because I also had a question about the computational tractability when you go to several agents, which you have in traffic.
Yeah, so exactly doesn't, I mean, it's a well-known bottleneck, but you can do some by cleverly using system decomposition.
Okay. Penger, you want?
Yeah, so that's quite a number of questions already answered. I guess since we're already on this slide, I actually had a question about the results on comparing the efficiency,
yes,
and the safety.
Yeah.
I don't mind if could you go to that slide?
Yeah.
It's a very nitpicky question. So I guess here I saw there is one point.
One green dot behind the yellow dot that is making
yes.
my plot less pretty. Yes.
Yes,
but it's experimental data, so I could not temper it. Yes, I mean, these are flukes.
Okay, so I was just wondering if there's any particular observations or insights there, but
not really. Not really. No, it's just somewhat outlier that happened during our tests. We test on a racetrack that is about 2 hours north of San Francisco, and you know, who knows, maybe there was, we thought a little bit about it. But so with experimental data, you're always going to have a little bit of outlier. Indeed, it's actually quite interesting how the points are so tightly gathered. It almost seems like an artistic rendering as opposed to experimental data. So I would actually counteract that actually the data is quite nicely clustered. We don't really know. It could have been a number of different things that go from maybe some noise in the perception module to some who knows what in the computations of the QP. Who knows? We don't know.
Cool.
But you have a keen eye.
I mean, I guess the one thing that we could say here also is that the direction in which it failed is kind of the right one, right?
Yes,
it lost efficiency and not safety. Yeah, right. So
yeah, that's a good point, Nick. Yes, so it would have been much worse if the outlier was in the y direction, because that would have meant a loss of efficiency. Sorry, a loss of safety.
Okay, I have another one. So, I mean, you have this separation of high-level planning and low-level safety control, right? And I was not I'm not entirely sure of how the stochastic predictions, like the trajectory paper, which gives you, I guess, distributions of human behavior. Is it used only on the high level to plan the path?
Correct. So basically, you get a distribution of, so in the simplest setting, we consider different motion primitives. Then we sample a distribution of human responses. We score by using an average, according to an aggregate cost function, the best motion primitive, and that becomes our planned trajectory depicted in this plot. So basically, all the probabilistic reasoning is inside the interaction planner. It does not percolate into neither the reachability cache nor the MPC tracking controller. You could think about ways to actually propagate this uncertainty lower, but we haven't done it yet.
Okay, so yeah, that was one of the questions I was aiming at, because I mean, on the lower level, you could do something, yeah, more stochastic, risk aware, I guess, in that sense, if you incorporate the predictions. Another question that I have, I read.
Yeah, I mean, but when you really are trying to enforce collision avoidance, and it basically means, so we plan at about 100 to 300 hertz. Mm-hmm. Sure, you could do it. You could consider chance constraints and so on. But at that level of the control hierarchy, first of all, it's computationally complex. And two, making probabilistic guarantees stochastic at the collision avoidance level, it seems quite dangerous to me. We've done a lot of work in the chance constraint planning area. And I have to admit that in general, I'm not a super fan of the chance constraints for a number of reasons. One, they are extremely complicated mathematical objects. You oftentimes resort to approximations that can be very coarse. Two, they still rely on a number of assumptions about how you model the stochasticity. So in a way, they give you also a false sense of safety, right? So the question is, does it really pay off? So that's why, at least in this work, we prefer to go with really worst case reasoning, but in a way that still allows you to reason about a sentient agent and glues well with the higher level probabilistic reasoning.
Mm-hmm. Follow-up question. I mean, I read that these that you can predict human behavior up until 400 milliseconds, into the future. What is your observation, your experience from there?
In our work, we go to about a couple of seconds in the future. Okay. Then 1 to 2 seconds. But then, of course, it also depends a little bit on the scene, on the setting.
Right.
Beyond that, it starts becoming not very accurate anymore. But on the other hand, you don't really even care about it anymore, because when you are a few seconds away from where you are, I will claim that you do not really need this sophisticated way of modeling interactions. So we found 1 to 2 seconds, at least for self-driving cars. I mean, I'm not saying that you don't do predictions beyond the 2 seconds, but you just rely on simpler models. For example, you just forward propagates the dynamics, maybe using an EKF and so on.
I had a question about trajectron plus. So you talked about these phenomenological models, and they can model these multimodal behaviors in humans. But is there any way of assigning a level of trust or risk to the output of the predictions? Because here, mostly you're doing like empirical evaluations on the trajectories that you output, right?
Yeah, so first of all, we have distribution information about the predictions. How those predictions are calibrated, that's actually a fantastic question that we just started looking at with a colleague here at Stanford, Silvio Savarese, who is doing some work in the area of calibrated uncertainty. So the short answer is no, but it's something we're looking into. That's a very good question.
I have one. Oh, Nick.
And that's in general, though, one of the reasons why oftentimes I prefer to use uncertainty information more in a cost function rather than as a constraint. Because in the cost function, as long as the uncertainty puts you in the right ballpark, it allows you to drive the selection of a control in the right direction. In a constraint, you have a much more committing way of using uncertainty. And so it's questionable whether actually we have such a characterization of uncertainty. It really allows us to reason in a way that constraints would really force us to reason.
It seems like this is very closely tied into kind of the direction of future work that you discussed in terms of how do you propagate uncertainty from the perception to the planning level. But I guess what I'm maybe having a hard time squaring with here is if you're concerned with, say, safety critical planning, then if you're only using the uncertainty, say, in your cost function and not in your constraints, how do you then consequently say something strong about safety?
I don't.
I
always said in my talk is safety assurances, never safety guarantees.
Right. I see.
No,
okay.
I was in my talk. I'm always very careful, always mentioning safety assurances, but never safety guarantees. No, you're right. I mean, we cannot claim any safety guarantee for a number of reasons. First, because the uncertainty may not be calibrated. Second of all, because of course there are issues of generalizability of our models. Third, because right now we're not accounting for the uncertainty from the upstream perception module in something that we are trying to do right now with Silvio Savarese here at Stanford, but we're not doing it now. So basically, all the uncertainty that comes from the perception module is right now. And I would say it's very common to most trajectory forecasting models is removed. So yeah, absolutely. We are not claiming any. And of course, then we are using a bunch of tricks in the MPC routine in order to make sure that the MPC problem is feasible. So if you see here, we have all these sigmas that are slack variables, so which also might compound in what type of guarantees we can really have. So the bottom line is no, we reason about safety assurances. I think is an open question if you can really reason in terms of safety guarantees specifically for such complicated problems that entail interaction with other humans and so on. So there is so much uncertainty that it's very hard for me to see how one could possibly, we can indulge on the idea, but I think it will be very hard to.
Sure, I think my follow-up question was going to be is asking for safety guarantees even a well-posed question in the context
I don't think so. I don't think
of
so.
Systems with humans in the loop.
I don't think so. As I said, we can indulge on the idea, but I mean, at the end of the day, if a human really decided to drive in a completely crazy way, it's going to collide with us. There is not much we can do. If you want to avoid it, really, and this is also something we observe with our experiments, you should just stay put. So yeah, so I think in my mind, when people talk about safety guarantees and so on, in the context of interactions with humans, it's a little bit of an impulse problem and a little bit of a misleading statement. I think that more humbly, we should reason in terms of safety assurances and try to do the best we can with this concept, to be very clear in all the assumptions that we make. And that's why in my work, I like to compartmentalize the different models, because it really allowed me to make clear all the assumptions that go into each module.
Marco, sorry, my computer just crashed. Great talk.
Hey, George.
Can I ask a question about the STL and neural networks? I didn't get a sense if it was a synthesis approach, a training approach, an analysis verification approach. Can you tell us a little bit
actually,
more?
It's a fairly general tool. Basically, what you do is to take a signal that you want to obey some simple signal temporal logic formula, and you show how the computation of the robustness trace for this signal can be reframed as computation over a computation graph that is typically used for deep learning. At that point,
so you're using the neural network to learn the robustness trade-off, or you're just...
So once you make this translation, then you can use...
you can do a variations of problems.
Exactly. You can do this thing in a variety of settings. You can, for example, train for both prediction accuracy, meaning you want your neural network to optimize some loss, but at the same time, you want to make sure that you minimize some robustness loss with respect to a formula, so that basically you constrain what the output of the neural network could be. You could do it for the purposes of trajectory planning. If you want to have a neural network type of planner, you can use as a way to try to uncover some logical structure in your neural network. So it's very general framework. So there are a number of ways this could be used. I think I've just been scratching the surface. So I'm actually quite excited about this area of research. It allows us to peek with a symbolic tool into neural networks.
Great, thank you. I'll take a look at this. This looks exciting.
Yeah.
Thank you.
If you have any questions, please let me know.
I'm sure Lars does. And...
Yeah, I do. So yeah, I've been working on STL quite a bit with Dimos at KDH. So
you have also the local expert, Jana.
Yeah, right. Jana is there too. Yeah. So so this STL CG kind of represents the STL specification, right?
That's right. Well, translated into view it as a sort of a translation tool, whereby you translate the computation of a trace into basically a computation graph computation. Okay, so what it gives you is if you put in a signal, it will give you the robustness in there, or what do you? Correct. Okay. Yeah. Okay. So it's somewhat like, I mean, there are timed automata, right, that represent STL specifications, for instance. Oh, yes. Yeah. It's not that it's to do the computation of the robustness, you could do it in many different ways. For example, by using automata. Here, the idea is to do it in a way that speaks the same language that the neural networks speak. Yeah, yeah. That's the whole point. Yeah, and then you can combine them nicely. I will... Exactly. So it's not doing any magic. It's not a better way of computing robustness and so on. Absolutely not. It's just recognizing that actually can be fairly naturally. Also, it's a relatively simple translation. Translate this in the same language that you use to train neural networks. Yeah, thank you. Sure. And yeah, if you have further questions, let me know. Yeah, I will definitely look at the paper. And yeah.
Hey, great. Well, I'd like to thank everyone again for attending today's talk, our panelists for the questions and great discussion, and of course, Marco for a fantastic talk. And I'll hand the reins over back to Gabby to wrap things up.
Thank you so much. And thank you again, everyone, for joining us here today. I would like to let everyone know that tune in next Friday for, actually, it's not next Friday. Tune in Friday, December 4th at 11 a.m. for the next Grasping Robotics speaker, Dr. Aaron Johnson from CMU. And for more information on upcoming events, be sure to follow us on social media or check our website. Thank you again and have a wonderful day.